All right, so last week we started with vectors, and we are going to build on it or upon it to get to the level that we're able to get deep understanding of this amazing field, which is linear algebra. And last week we got to know that machine learning, AI actually depends or are built on this mathematics. Okay, so today we want to continue from where we left off last week. Last week's own was just vectors where we learned some stuff. Okay, so today we are taking inner product, orthogonal, and norms. Now for this module, we will spend 2 weeks because it's a little bit theoretical. Okay, we need to understand the concept, and with the concept, we're able to understand where we can apply these things in our machine learning journey. All right. So I'm going to give a poll right now. Okay, whatever you learned last week, if you heard something anywhere, just type in the chat. Okay. So um, what did you learn last week? Okay. So you kindly. Okay. All right. So what did you learn last week? Whatever you heard, okay, you can go on and type. I just want to know what you learned before I start my lesson. All right. So maybe 2 minutes. Let me say 2 minutes. Whatever you learned in 2 minutes, just share with us quickly. Okay. Yeah. I just want to, okay. Be specific on it. You say vectors precisely. What did you hear? Okay. Just be specific on it. We say vectors. Yes, we learn about vectors. But what did you hear? Specific things. Just be, specific with your answer. Yeah. Yeah, vectors is broad. So let's be specific. Ryan said, I will know, okay, you were in part because you are not around. Do again. Hmm. Okay, linear algebra method like allow faster computation of systems. Okay, and the basics help us to get more information about data. Okay, I couldn't join due to technical issues. Okay, who again? Um, um, okay, I couldn't join. Vectors are used to present and manipulate data. All right, you need vectors to build. Okay, you need vectors to build so innovative. Okay, then we learn about vectors being okay. Learn about vectors. We learn about vectors being okay, being about mark design direction. Okay, you need vectors to build something innovative with machine learning. Okay, vectors are used to represent data, manipulate data. Linear algebra allow for further computation. Linear algebra calculus. Alright, vectors are a list of numbers where the pose of matters. Okay, I learned that basis helps to get more information about data. Okay, so that is what some of you learned. Please, it's good you share. Okay, it's good. You share whatever you learned. All right, so don't just, just be a, how do you call it, a spectator. Just type something, write something, whatever you learn, just share with us. Okay. So someone said there are four accounts when you multiply a scalar by a vector. Okay, so you can stretch it. So we stretch it in the direction of the vector, okay, or you can stretch it the opposite. You can also decrease it, okay. Okay, so we learned a lot, and we are going to build on it, or we are going to build up on it, okay, so that um, Okay. We are going to build upon it so that it will be a continuation from last week's lesson. Okay. All right. So still our motto still stands. Okay. The only news you have, that means you are here for knowledge. So make sure you strive and also get to know and understand all the things that we are doing. All right. So our timeline still holds from 10th October all the way to 14th December. All right. So our lectures Sundays, as you all know, 7 p.m. to 8:30 p.m. But we made it 9. Should we go beyond the 8:30? Then labs also Saturday 7 p.m. to 9 p.m. All right. So this is what we're going to talk about. But as I said, this session we are going to use 2 weeks. Okay, so we'll talk about inner products, then inequalities, then also orthogonal vectors and orthogonal base. So today we are going to talk about these three. Right, so these three talk about. Then next week we pick the last, four and deal with them. Right. So today is this three. But as I said, it is more of theoretical. So I will encourage you to have your book or your book and a pencil with you so that you can put down some stuff for your own understanding later on. Okay. So let's recap. So we learned that vectors, they are ordered list of numbers, okay, and their position matters a lot, okay. Their position matters a lot, as someone said, and they are used to represent features or characteristics, okay. So what are some of the features? You can talk about somebody's height, somebody's weight, the complexion, or uh, what again? The gender or sex. And they represent a single data point. So a practical example is if you take a house, or maybe, yes, a house that is for sale, or a building that is for sale, okay, we want certain features that we could use to be able to build uh, some features so that our AI model or our machine learning model will be able to what? Extract those features, be able to make a decision out of it. So what are some of the features? We have size, we have the number of bedrooms, we also have what? The ages or years, then also the distance. Okay. Now, all these things are things that we can put in a form of a vector. So if you look at this, we have a scenario over here that says that house A might have the following features or characteristics, which is the square area of the building, the number of bedrooms, okay, the years of the house, okay, then also miles from school. All right. So this is in a vector form. Okay, and last time we learned that we prefer to write this on the column vector. Okay, although we can write in a row vector, but we prefer this on the column vector because that is what is better, or that is far better than the row. Okay, we can also have a different feature characteristic, the same thing with the same scenario, but different element or different values now, as you can see. So that is another vector, which is also different from the first one. So last week, that's what we learned, that all these features or characteristics, we can put it in a vector form. And once we put it in a vector form, we can apply certain operations. And that is where we spoke about the vector species. All right. So when you take a vector, it can be represented geometrically. So the first one, as you can see, is the two-dimensional vector or plane or Cartesian plane that we all know. We had it in high school, where we have two axes, the y and the x axis, where you have your coordinates, which we can be written in the form of a vector, and we can draw our vector. Now, we said it has a direction, and last time we learned that the direction shows you where the vector will land. So we tell you that this is where it's heading, so it's going to land over here. Then from the 2D, we went on to the 3D, where the 3D, we introduce another axis or dimension, which is the Z. So this is your height, okay? So this is your Y, and here is your X, right? So this is a plane, but it's a 3D, okay, which is a full cube, okay? Can be a full cube or a cuboid, right? So it's the same thing, but it is just that we have introduced a new dimension, all right? Then this is a fourth dimension where things have changed. So trying to view things over here is quite difficult. But as I said, we humans, we can only end at the third dimension. Fourth dimension becomes difficult. It is the same ideology that we try to scale it to features that can go or span all the way to the 100 or even the 1,000. Okay, so what can be done over here, which is for the two-dimensional, and what can be done in the third dimension, we can scale it to any dimension. All right. So all we have to do is to understand the first, the second, and the third dimension, and we can scale it up to any dimension of our choice. And that's what you did yesterday in the lab. All right. So we said vectors are ordered lists, okay, and we can represent them in a two-dimensional, in a three-dimensional, or in an n-dimensional. But it's just a set of numbers, and this set of numbers, they need to agree, or they have to follow certain rules, and these rules is what we use to define them. Now those of you who took the quiz, you realize that machine learning need to, anytime we are doing any machine learning, we need to stay within a specific space. You don't need to go outside, okay? And that is where vector space comes in. So the vector space just talks about the rules that we have to follow when we are doing any operation with regard to vector. So the first thing we have to deal with is we need to have our set of vectors. Then we have all the operations has to be filled. I mean, if I say filled only deals with two operations, addition and multiplication. Addition and multiplication. We don't have division, we don't have subtraction over there. So the first rule, as you can see over here, is when I add two vectors, I still must be in that vector space. So addition works in vector space. Adding two vectors, you are still in that vector space. So what are these? The first one is the commutative property. So when you add two vectors and you interchange it, okay, it is still the same. Now, the associative property, when you try to group, which is I group the second, I add it and add it to the first, is the same as grouping the first two and adding to the third, associative. Then, when you take any vector, we can add it to a null vector. A null vector, that is zero, okay, everything, or all the elements, they are zero. When I add it to a null vector, I should get the same vector. Then we have the next one, which is the additive inverse. That is the subtraction. We don't have subtraction in vectors, but the additive inverse enables us to be able to subtract vectors. So when we have a vector, we can have it inverse, which is the negative of it. So when I add a vector to its inverse, it's the same as you subtraction, or you are subtracting. Okay, so a vector plus its inverse is a null vector, which is zero, as you can see over here. All right. Then the next one is the multiplication. So we say when you take the vector space, okay, one, we said the vector, it shouldn't be an empty vector, and it has to follow two operations, the addition and also the multiplication. The addition is what I've shown. So let's talk about the multiplication. So for the multiplication, we are talking about scalar multiplication. Scalar multiplication. So here we have a vector x over there multiplying by another scalar. It's the same as multiplying the two scalars and getting the results to multiply the vector. Okay. I can have two vectors and the scalar can distribute. It's like expansion. Okay, the scalar can multiply the vectors individually, and I will still be able to get my answer in the vector space. And the last one is when a vector multiplies one, is the same thing. So we call this one, this is the identity element, okay? Because one multiplied by, a number is the same number, okay? So the one there becomes our identity element. So this vector space that we are talking about, it need to, follow all these rules stated over here. Okay, if you have a vector and it doesn't agree to these rules, it can't be part of the vector space. And last time I gave you a typical example that let's take the natural numbers, the natural numbers space. Natural numbers, we start from 1 all the way to infinity. So when I add two natural numbers, I have to still get what? A natural number. But when I try to do subtraction, I will go negative, and the negative will not allow me to be in a natural number space. So negative cannot be part or cannot be an operation that we can use for natural numbers. Okay. When I multiply two natural numbers, I will still get a natural number. So addition and multiplication will work for natural numbers. It's the same ideology that we are using for the vector space. That if you take a vector space, okay, there are certain rules that we have to follow. First, the vector should not be empty. Second, addition works. That means when you add two vectors, you will still be able to get a vector. Then when you multiply a vector by a scalar, you're able to get a vector. And we saw the other, properties where you saw the additive or the inverse of it. We also saw the associative and also the commutative. Okay, so all these things are, rules that are able to guide vectors so that operations that we do will be able to stay in that space. Right. So this is how we represented last week. We did that. Let me skip it. Okay. All right. So after that, we also went to vector spaces. And we said you can have your vector, but you have a subset of it. And last time I used another example to explain that when you have your natural numbers, when you take natural numbers from 1, 2, 3, all the way to infinity, right? We can get other number system from our natural numbers, such as even numbers, such as prime numbers, such as odd numbers, such as multiples of 3. All these things are what? Subsets. So we can call them subspaces. Subspaces. So when you have a vector, we can have subspaces of this vector. Okay, and these subspaces, they all should agree or they should be able to follow the rules that are stated. What are some of the rules? Addition and also multiplication. Okay, so whatever subset that you pick from your vector space, that subset should also obey the addition rule and also the scalar multiplication. If it doesn't agree to it, it is not a subspace. All right, so we learned that the vector itself and also the zero vector is a subspace of the vector. So a typical example is, let's take a set. Let's go back to SS and also GHS. When you have a set, they can ask you to get the subsets of the set. So let's assume I have a set here, which is 1, then let's say 2, then 3. Okay, so I have a subset over here. Sorry, I have a set over here. Sorry, I have a set over here. If I want a subset, the first subset is going to be what? An empty set. Okay, so a null set is always a subset of this, and the set itself is always a subset of the set. The same ideology is what is being applied over here. So when you have a vector and you want to get a subspace out of it, the vector itself is a subspace of itself. And the vector 0 is also a subspace of the vector. Okay, so that is that. So when you take a two-dimensional vector, we say it's having 3 subspaces. The first one is the 0 vector. The second one is a line that passes through the origin. And the third one is the entire vector space. the entire vector space. So when I have a Cartesian coordinate over here, okay, now the zero vector is at the origin. Then we set a line that passes through the origin. So this is also a subspace and the entire vector space, okay, which last time we learned that we can use the basis to represent that. So with the basis, okay, we can get the entire vector space. All right, so that is that. So when you look at this diagram, you see that this is why is this not a subspace? I want someone to tell me why this is not a subspace. You can write your answer in the chat. Why what I've circled over here is not a subspace? Okay, and why do you think this one too is not a subspace? Okay, so let's take with the first one. So here's number one. So send the send the answer in the chat. Why is the number one not a subspace? I want someone to tell me why you think it's not a subspace. Please, I want all of you to participate. Whatever you know, just go ahead. Okay, I understand. All right. All right. So I still want my answer. I've heard you the slides. We'll talk about it. Okay. Why is the first one not a subspace? Why? Or just type it. Type it in the chat. Okay, just type it in the chat. Joshua, just type it in the chat. I want two or three people. Let's be quick. Let's be quick. Let's be quick. Let's be quick. Okay, Joshua. All right. Okay, then you can go on and yeah, talk. You can go on. Yeah. Joshua, you can go and talk if you can type.
Can you hear me?
Yeah, I can hear you. Go on.
Okay, they are not closed under scalar multiplication.
They're not close under scalar multiplication. What I've circled.
Because if if you multiply it with negative, the first one, it will go out of that space. While for the second one, it is also not
Okay.
uh, closed under vector addition. Yes.
Can you come again? Because I'm a little bit confused with the answer. The first one, can you come again with the first one?
It
The
is
first
under
one.
scalar multiplication. It is not closed under
Okay,
scalar
why?
multiplication.
Okay, can you explain it?
Because if we multiply it with a negative scalar value, it will leave that space.
Okay, you leave that space. All right. And the second one?
It is not closed under vector addition. No, because it's not.
Okay,
Yes, it is not closed under vector addition.
why?
Because you can't use vector addition to move from one point to another in that space.
Okay. All right. Okay, thank you, Joshua. Okay, so let me read. The first one says it's not passing through the origin. All right. That is smart there. Then Emmanuel is saying that it's not a subspace because it's not close under the vector. Yes, it's not close under the vector, but why? There's a reason why it's not close under. because this dimension does not belong to the subspace. Okay. All right. So if you check the number one, let me name this one number two. Okay. Now let's go back to the slide where we spoke about this. Now we said for the two dimension we have three subspaces, right? The first one is the zero vector, which is a point at the origin. And the second one is the line which passes through the origin. And the third one is the one that will span the entire uh, uh, space, which is the two bases on the individual axis. Okay. Now, when you look at this diagram, you will see that yes, this one is a subspace, as you can see, because it's a straight line that is passing through the origin. All right. Now, the second one, as you can see over here, this is our zero vector, which is a point, which is the origin. But if you look at this line, look at where this line is. Okay, and if you look at this, the first one, the line is supposed to pass through the origin, but it's not passing through. It just ended over here, okay, which is going to this side. Okay, so that means it's only in this direction, okay, which from our definition, we said it passes through the origin. So we expect it to span towards the negative part, okay, which is always only giving us what? This. Okay, so because of that, it's not going to be part of our subspace. Okay, now if you look at this line also, we expect it to pass through the origin, but look at where the line is passing through. Okay, and because of that, we are not going to get uh, the operations that we spoke about. Okay, so it's not going to favor all this, so it will not work. So it is only this and that. As you can see, this, when we draw our bases, okay, we were able to get all the vectors over here, okay, because it will span the entire space, but this will not. Okay. Now for the three dimension, do we have a diagram for it? I remember I put a diagram. Okay, no, I did not. So for a three dimension, okay, so let's look at, we have four different types of subspaces. The first one is a point. So if you have your three dimension, okay, the first one is going to be the point, the one in the origin. So this is one, okay. Then the line that passes through the origin, then the plane, okay, then the entire 3D. Okay, so if you look at it, it's like we are building the vector, okay, from the zero dimension all the way to the dimension that we are dealing with. So we first talk about a point, which is this, then the line that passes through the origin and your plane. So if you're taking your plane, that means the z-axis will not be considered. So we just look at whatever plane that we have over here. Okay. But the moment we want to take the entire three dimension, that means we need to consider the basis. Okay. So that we're able to construct any vector that we want. Okay. Now all these sub uh, spaces, they will all may follow the addition and also the scalar multiplication. Okay, if you should do it right now, you see that if you have, let's say, a point, okay, when you multiply, if you add, you are still going to stay in that vector. You are still going to stay in that vector. All right. They also spoke about the linear combination and the span, where we said that when you have a vector, it can also be written, okay, in this form, where we have a vector and we multiply it by scalars. Now, as you can see over here, we have a vector W. Now, this vector W can be constructed using a lot of vectors, okay, but each vector multiplied by a scalar. Okay, each vector multiplied by a scalar. So that is a linear combination. So I have my vector W and I can reconstruct my vector W again using several or a set of vectors, each multiplied by what? a scalar, which as you can see over here. So this is a linear combination. This is a linear combination trying to express, okay, a vector, okay, in other using other vectors. Okay, trying to express a vector using other vectors. Okay, so that is that for that. Now with the linear combination, we spoke about the span. Okay, so we said the linear combination provide a way to take a small set of vectors and generate a whole lot of them. So let's go back here. Now when you take our vector W, we can create several vectors out of which is a V1 all the way to Vk. Now the set that we have, okay, we said we are creating something as spanning. So the set that we generate is known as your span. The set that we generate is known as your span. So which is the V1, the V2, the all the way to Vk. That is our span that we created. So if I have W, okay, it can span some vectors. Now, if we can span some vectors, then these vectors is going to be a linear combination that when you multiply it by a scalar, I should be able to get my W back. Okay. So the span just tells you the set of vectors, okay, from your combining vectors. Okay. So we have a diagram over here. Last time we spoke about it, where we said when you have a straight line, okay, we can have span on it. So if V1 is my vector, okay, I can have a lot of vectors on it. And as I said, it can be steps, okay. So if here can be one, you can also have one here. You can extend this one, you can have one over here. So if my vector is V1, okay, I can get V2 from it here. I can also get V3 from it over here. So my V1 is going to be V2, okay, plus my V3. But we said for us to be able to form that, it should be a linear combination. So we will express it using our scalar, okay, where this you use the basis to represent that, okay. So V1 can be expressed as C1, V2, then C2, V3, okay. So that is that. Now with the linear combination, when you take a Cartesian coordinate, okay, this we said should not be parallel. If it's parallel, it can't span the entire coordinate. So this any vector at all on this plane, you can construct it using this, okay, using this. All right, and that is what we spoke about, talking about linear independency of vectors. And we said that when you have a vector, okay, they are independent if this condition is satisfied. That means the only time this condition will be zero is when all the scalars are zero. When all the scalars are zero, it means that is the only solution. That is the only solution. If that is the only solution, it means this linear combination over here, the vectors over there are independent. We say they are linearly independent. But if C, which we, as we said, C1, C2, all the way to CK, okay, if zero is not the only solution for it, then we say that it becomes what? Linearly dependent, okay. And last week we discussed it, we said a set of vectors is linearly dependent if there exists at least one non-trivial solution, okay. That means when you compare or when you take the scalars over here, you realize that you can express one of the vectors in terms of the other. That's what last time we spoke about. You can express one of the vectors in terms of the other. All right. And in two-dimensional, okay, we say two vectors are linearly dependent if they lie on the same line. Okay, so if I have a vector over here and they are lying on the same line, okay, so let's assume this is V1, okay, this is V2, It will surprise you that if I multiply V1 by some scalar, I'll get what? V2. So we say that they are linearly dependent because one of them, by multiplying one of them, I'll be able to get the other. And that is what we don't want. That is what we don't want. All right. And for two vectors to be linearly independent, which is still talking about the two dimension, that means they need to point in the same direction. So one goes here, one goes here. That is where we say they can span the entire Cartesian plane. They can span the entire Cartesian plane. Now for 3D, we said three vectors are linearly dependent if they all lie in the same plane. Now remember, 3D, we have three different axes, okay? So even if two of them lies in this plane, okay, we say that they are linearly independent, okay? They are linearly independent. But if they don't, okay, they don't lie in the same plane, that means they are all pointing in a different direction, as we can see over here. Okay, then it becomes what? Linearly independent. Then we also spoke about the bases, and we said the bases are very important. They are the fundamentals, okay, because from the basis that we try to, have our linear combination and we try to construct or come up with any vector. And we said for us to have a base, one, it should be linearly independent, then it should span the entire vector, okay, space. And we saw that when you take the two dimension, the basis that we dealt with was this. Okay, so when you have this, which is 1 and the 0, and also the 0 and the 1, he said we can get any vector in the Cartesian coordinate or plane and get any vector by combining it with some scalar somewhere. Then we also saw this for the 3D, and we said this one also, by combining this with some scalars, we can have a linear combination, and with this linear combination, we can span the entire 3D space. All right. Now, not only these two, but we will also have other bases as well. As you can see, we have this and we have that. And last time we learned that the base is like a perspective, okay? So for this, we all know this because that is the Cartesian coordinate and this is the 3D coordinate. But we can also have a different base, and these different bases, so we are changing your perspective. And last time we learned that sometimes it's good to change your base so that you can learn a lot from your data. Okay, you can learn a lot from your data. Okay, and we also discussed about the dimension. All right, so with the dimension, we saw that when you take this, okay, because we have two bases to represent that, which is your I over here and your J over here, okay, we lead us to our two dimension. Then when you take your 3D, okay, you have our, this is your J, this is your K, and this is your I, okay. So we need these three to represent. So that is why we deal with our three dimension, okay. The n dimension talks about, the number of dimensions I have. But as I said, we cannot, visualize. We only visualize to the third dimension. Okay, hyper or higher dimensions becomes a problem for us. Okay. All right. So a plane through the origin in 3D is a subspace of two dimensions. Then a line through the origin in 3D is also a subspace of one dimension. And the space containing only the zero dimension has a zero dimension. So he's saying that when you have a plane, okay, when you have a 3D and you have a plane, okay, the dimension, although we are dealing with a 3D dimension, but the dimension for the plane is 2. Because a plane, you need what? Two bases to represent it. Okay, a plane, you need two bases. And if it's a line, okay, a line you just need only, so like a number line that we all learned in school. Okay, so just one dimension can do. Then if it's a zero or a point, that is just a zero dimension. Okay, that's just a zero dimension. So these are our or what we spoke about last week. All right. So today, let's start. So I have a quick question here. Uh, how many classes are shown, and can you summarize, your reason in a single sentence for me? So let me create a poll right now. All right. Then you just type your answer. So how many classes are shown? All right. Let's be quick. How many classes are shown over here? If you look at this diagram, how many classes are shown? Okay, someone said two. All right, two. Let's be quick. Two, two, two. Okay, someone said Joshua said five. Okay. Okay. So 14 out of 33. Please, let's all, do something. Hey, someone said three. Okay. All right. So I think we're getting more people saying it's two. All right. So the follow-up question. Um, all right. So the follow-up question is, can you summarize your reason? Those of you said two, 14 people said two, two people said five, then one person said three. So follow-up question, can you uh, summarize in just a single sentence? Summarize your answer, reason in a single sentence. Okay. So go on and do that quick. Those of you said I've published the results, so I saw it. So those of you said, what is it? Yes, those of you said 14. People said two. So I need more answers. 14 answers. Then two people said five. Then one person said three. So I want explanation. Okay. All right. So there are two clusters. Oh, but you said two. Is it there are two clusters? Mariama, okay. Agabe said the point seems to concentrate on two main regions. Okay. The point they seem to consider are two main regions. Okay. Manal said because the points are distinctly clustered. Okay. All right. Two groups of data. But how will you know? Daniel, how will you know there are two groups of data? Okay. I'll go. Albert's answer is. Is okay. Say the points are seem to consider two main. Groups of places. Right. There are two distinct course titles listed under 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 with two. Hey, Abigail, I don't understand your answer. There are two distinct course titles listed under with two. Hey, I'm confused. I don't know what you are saying. Okay. So okay, Joshua said okay. Petals with is a class, and petal is equal to five. All right, then there are two distinct groups. Hmm. Okay, so it's okay. Now, if you look at it carefully, you will see that. Okay, so let me answer the poll. Now, if you look at it carefully, you will see that yes. If you look at this point over here, and let's look at this point over here. Okay. Now, the reason I have, people are saying two. I'm not saying if you said five is wrong, but if you look at it distinctively, you are going to see that we have two clusters, right? Now, these ones, they've been clusters together because they have I mean, similar features. Okay, but the main reason why you see them classes together, somebody will say that show me your friend and I'll show you your character. Show me your friend, I'll show you your character. So they are the distance between these classes, okay, from this is quite far or large. That is why these ones are together. And if you look at this, they are also being clustered together. So they are also together. That means the distance between these points is closer as compared to this. Okay. So one of the things that you guys are going to see a lot or face a lot is norms and distances. All right. Now, last time when I asked you guys to define what a vector is, some of you said it's made up of direction and it has what magnitude. Okay, so the magnitude we talk about the length or the length. Another term, okay, somebody also will say norms, okay, the length. Now, one of the things that is important to machine learning engineers is this term. Okay. Now, for us to be able to know the distance between two vectors, we need to find a way to calculate it. And that is where the norms comes in. So it's just a function, you give it a vector, but at the end, it will return a scalar value that represents its magnitude. It will return a scalar value that represents its magnitude. So we have different norms. We are going to talk about it, but they are of very, very important significance in machine learning. One of them is error calculation, which you guys will do, okay, where you want to calculate errors. So you have your actual value. You also have your predicted value, okay. So this is your actual value, this is your predicted value. How for you to know that your model is learning, you have to be able to calculate, I mean, the distance, which is the norm between this, able to know whether you are getting close to your actual value or you are getting, I mean, far away from it. All right. And we also talk about regularization. Okay. Yes. I don't we start using some of these terms, but I mean when we start, I mean working seriously, we will come across this. Okay. But remember that norms are used, okay, to be able to help with model regularization. Right. So the first one I want to talk about is the Euclidean norm. This is all done in before in high school, which is the Pythagorean theorem or the Pythagorean triple. All right. So the L2 norm, you see this, okay, in papers, in manuscript, you know, you mostly see this a lot, okay, where it is expressed as this. So when we have a vector, okay, which is a vector x, and it's having this element, this one is having two elements, so which is x1, x2, according to the formula, which we will look at how it came by, this is how it is expressed. So I have my norm, which is my Euclidean norm or the L2 norm, as the square root of the first element, the square root of the first element plus the same square root. Okay, that means you have a bigger square root, then you have the square of the first element plus the square of the second element. So by looking at it over here, you see that this is the distance for my x1, then this is also the length, maybe the length for my x2. So if you look at it carefully, this is the Pythagorean theorem or triple, which we say the square of this distance plus the square of this distance is the same as what this. And that is what has been expressed over here. Okay, so the square root is what, I mean, we put it on it. Okay. Now, mind you, even if you are having three different entities or three different elements, okay, if you're having three different elements, we can still apply the same thing. Okay, we can still apply the same thing. So this can be scaled to where we are having n different, I mean, elements. So having n different elements, okay, mathematics, we can scale it. We do it for one, we can scale it to others, and it is the same thing. So if you look at it, it is x1 squared plus x2 squared plus x3 squared all the way to xn squared, then you put your square root on it. So with this, you're able to find your Euclidean or Euclidean norm, sorry, the L2 norm. All right. So this is that's as you can see over here as I showed you with the calculation. Okay, so this is Pythagorean. So when you can do that, that is what we have over here. Okay. The same thing with the 2D, sorry, the 3D. Okay. Now the next one is the L1, which is the Manhattan norm. I don't know whether I did pronounce it well. But okay. So with this one, it's quite different from the L2. For this, all our or what we are focusing on is just we want to find the absolute value. Okay, you know what the absolute value is. When you find a difference and it's still negative, you just take the positive. Okay, so this is quite different. There's no square over here. We just find the difference and we just return the absolute value. With this, it can also be extended to the same number. The it can also be extended to the number n over here. Okay, so if you are dealing with n uh, elements, it can be extended to that. Now, why do we have these two? Now, if you look at this, if you look at this diagram, this we move in blocks. Okay, so we move in blocks for this, but this is what we say we use or the Euclidean or we use the Pythagorean triple or the Pythagorean theorem to do that. Now, why do you have to, spend time working on this? Because one is able to help us to work on similarity. So how will you know that two data points are the same? Okay, the distance between them, be able to know, and also control complexity. That is why, if you look at it, when I ask you about these points, okay, some of you said that we have two clusters over there. So because of the similarity, okay, because they are similar, they are going to have what? A lower distance between them or a lower norm between them. So they're going to cluster together from the ones that's not close. Okay. So if you look at the norms, we can use it to be able to find how similar two data points are or data points are. All right. The next one is the distance. Okay. Now, this is quite different from the norms. Okay. The distance, we just want to take two vectors. We are considering two vectors, but the norm is only a single vector that we pick and we do that. So if you want to know the distance between two vectors, that one is we are dealing with the distance. But if you just want to know the length of a vector, that is where we talk about the norms to take or know the difference between the two. So it follows the same thing, but just that the formula changes. It's just the same formula, but how the formula is written changes. So if you look here, we are using D, okay, and it follows the same thing. But this time, if you look at it, the difference between the two vectors that you are dealing with, okay. We can also scale it up to n or a lot of vectors. So if you look at it, it's the same formula that we have over here, but it has been scaled up. Okay. Now the same thing with the L1. So that one too, if you want to find the distance between two vectors, okay, it's the same thing we said about the absolute value. So you find the difference between the two vectors and we can get the absolute value for it. Okay. So look at the two. Please know the difference between the norm and the distance. Okay, they are not the same. All right. One of it, they all give us a scalar, but look at how the two of them are calculated. Okay. Okay. Now we have this, but we need to understand. Now this one, okay, is preferred because it uses the absolute value. So normally we call something outliers. Okay, when the data is maybe deviate from the abnormal or from the standard. Okay. Now, when you try to use the Euclidean distance or even the Euclidean norm, because we are squaring the thing, okay, it try to scale up the outlier. So outliers become very sensitive with the Euclidean distance or even the Euclidean norm because we are squaring. So we square. But because here we are finding the absolute, okay, is less sensitive to, outliers. Okay, so one thing about machine learning when you are dealing with linear regression, that sometimes you have, some of these ways that you want to, calculate your errors, and we have a lot of them over there, and each one has its own advantages and disadvantages. So if you look at for this one that we are dealing with, okay, one of it is able to, or one of it is less sensitive to large differences. The other one is what? Uh, Sensitive to a large difference. So you are the one to choose. And if you look at it, see, we now understand that because we are finding the distance between two, vectors, okay, if we have an outlier, so an example, let me see whether I can get a space to explain this. If you have an outlier, so let's assume we have ages of students. So 7, then 4. Oh, no, 4 is bad. So let's say 7, then let's say 9 here. Then all of a sudden, we go and get something like 19. Now, you agree that if you have somebody who is 7 and 9, the person will run maybe class 3 or grade 3, okay? But 19, that is an outlier. Okay, so if you want to, find a distance between this, you do it, for example, if you want to find a distance between this and this, okay, you are going to get 10. If you square 10, that is 100. You see the way it has increased the value, right? But if you use this one, you are just going to find a difference. The difference is going to what? It's still going to be 10. And it's not going to have, much effects on the way your model is going to learn. So now that we are done with the Euclidean norm and also the norms and also the distance, we are going to talk about inner product. This is what we want to do today. Okay. Now, inner product is similar to what we spoke about, that if you feed the norm, if you feed a vector, okay, with the norm, or if you feed a norm, a vector to a norm, okay, you get a scalar uh, value out. The same thing apply over here, but because we are dealing with vectors, we have rules. Okay, we have rules, we have axioms that we need to follow, be able to make sure that any calculation that we do, we stay within a specific space. All right. Now, last week we agreed or we learned that vector addition, subtraction, which is the subtraction over here, is the additive inverse. Okay. And the scalar multiplication, what they do is they change the position or they scale a vector. Okay. But what we want to talk about today is when you have a vector, okay, we want to find a way to multiply. But how do you multiply? We say when you multiply it at the end, what do we get? You end up getting a scalar. Okay, we end up getting a scalar. And how is it done? We have rules that we need to follow to be able to stay within that. And that is what we are going to discuss with the inner product. The inner product, we have a lot of them. Okay, one of them being the dot products. Okay, we will discuss as we progress. Okay, but the inner product is the general. So the dot product, all these things, they have to follow the rules that the inner product will set. So when you take the inner product, you see they are used to measure the similarity of data points. The similarity of data point. Next week we will talk about it known as vector projection. If you want to project one vector on another, we'll still visit the inner product again. The inner product is used to measure the angle between two vectors. Okay, but as I said, today we are not going to dive deep into that. Today we just want to learn about the theory, about some of these things. The next week we'll learn about the projection and we'll take a practical scenario regard to that. So I have two vectors, this and that, and I want to find their dot product. Their dot product. So how do you find their dot product? It's like multiplying the elements by themselves. So position wise. So if you have a vector, which is then 1, then then 2, okay. Then I have another one over here, which is W1, 1, then W2, okay. Now, from our formula over here, you can see that we just multiply this by this and this by that, all the way to what? To the n dimension, whatever the dimension that we are dealing with. This is the dot product. This is the dot product. So if you generalize it, this is what you will get. Just a summation of the element-wise multiplication. Okay. So when you take a dot product of a vector, that means a vector, you have a vector and you want to find the dot product of itself. Okay, so for example, I have a vector v and I want to find the dot product of that vector. It's just the vector multiplying itself. So as you can see over here, I have a vector here and I want to find the dot product of itself. Now, if you look at this, you will see that we are getting the Euclidean norm back again. Okay, so when you have a vector and you find the dot product of itself, you are going back to get the Euclidean norm, as you can see, because the Euclidean norm, when we go back, you saw that we find the square root and we square the elements and we add them in the square root. That is what we are seeing over here. I have a vector v and I want to find the dot product of that vector. Okay, so from the formula we saw in the previous slide, just multiply and we get this. So once we get this, it's similar or in the same thing like the Euclidean norm, and that is what I've been seeing over here. So as you can see, the dot product, okay, of this vector itself is just finding the Euclidean norm or the length of the vector. Okay, so as you can see, we have seen all these things already before, but there are some rules that we have to understand. The first one is when you find the Euclidean norm, okay, it shouldn't be negative. Okay, it is greater than or equal to 0. And the only time it is 0 is when the vector is a 0 vector. When a vector is a 0 vector, that is the only time you find out that the Euclidean norm is 0. Apart from that, it is greater than 0. Apart from that, it's greater than 0. And you will never get negative. You won't get negative. Okay, so with this, the dot products and the Euclidean norm, they all serve to inspire the definition of the inner product. So let's find out how the inner product is defined. How is it defined? All right, so if you take the inner product, you see it's a pairing that takes two vectors and produces a real number, which is a scalar, okay, and is required to satisfy some following rules or axioms. What are these axioms? Let's find out. The first one is the bilinearity, okay, bilinearity, and then the symmetry. Now, this is obvious. I won't waste time on it. It's like the commutative that we did, which is A, B is the same as B, A. Okay. Now, this is obvious. But this, I want you to pay attention carefully. What is happening over here? Now, I have this, which has been defined. Now, if you look at it, if you look at the left-hand side, sorry, the right-hand side, is a little bit like distributive in a sense that U will be used for this, then the V also will be used for this. Okay, the same thing over here, U for V, as you can see, then we have U also for W. Okay, now what it's saying is that in either way, whether it is from the left to the right or from right to the left, you will get the same thing. That is why you use the word bilinear. Bilinear. Okay, and we will prove that very soon. Okay, we'll prove that very soon. Then the last one is positivity. That means anytime you find the inner product, okay, the answer should be greater than 0. The only time zero is when the vector is a zero vector. When it's a zero vector, that's the only time it will be zero. Apart from that, okay. I'm Steven. Are you still on the call? Is it you can't hear? I'm coming. Guys, please, I'm coming in. A minute, a minute. Okay. Okay, so let's proceed. All right, so given an inner product, the associative norm, we can put it like this, okay? And this is what you saw for the Euclidean norm. So it has been written using the inner product for us. And these axioms has to hold. Now, for the Euclidean norm, this is what we saw, okay, that it can be like this. But the only time to be zero is when the vector is a zero vector, okay? When a vector is a zero vector, that's why it's going to be zero. Apart from that, is greater than zero. They also saw the bilinear. Okay, now how do you prove this, or how do you get this? Now, if you look at it, we have this. Okay, so look at the definition we have over here. So if you have a norm over here, we said we can express using what? The inner product. Okay, so the Euclidean norm, you saw that when we did the Euclidean norm, we saw something like this, okay, which we had our square root, then we decided to square them. So that is what has been put here for us, which is our v and this. Okay, that's what we have. Now, when we come here, okay, when we come here, this has to be defined, and that's what has been defined. Now, when we go on, we can multiply the scalars, and that's why we have the c squared, and we can find the square root of the scalar, and that one will come out. And this is what has been defined for us already here. Okay, so this is what has been defined. So instead of the square root of the inner product, we can replace it with that. So it's the same thing, okay? It's the same thing. Yeah. So that's why it's saying that if this is a scalar, okay, then if you multiply it, it has to be a homogeneous something, okay? That means it doesn't matter, we still get the same thing. The same, this is the same as, I mean, that. Nothing has changed. Okay. All right, so the next one is we have this. Now we have this definition, which is for our inner product, which you've already seen it. It's like a dot product already. Okay, so this is just a dot product. So we said you multiply this by this, then this by this. That has been expressed over here. Okay. Now, one thing about a dot product or the inner product is we can also have a weighted inner product. A weighted inner product is when we try to assign weight, okay, to our product. So we have our inner product defined over here, but look at the definition. Weight has been assigned to the individual product. So the product between the ones is we have 2 has been assigned to it. The product between the twos to 5 2 has been assigned to it. Now, why do we need this weighted product? Sometimes when you are working with data sets, okay, you have imbalanced data sets. And you work on a project like that, you sometimes want to what? Balance it, okay? You can try to do this, okay? Or sometimes also some of the features, okay, some of them are least significant. You want to make sure that they are significant. What you can do is you can try to, I mean, give them specific weight that will be able to, I mean, raise their values up or raise their features up. Okay. So when we have this, we can prove all these things. We can prove it. Okay. So let's try to see if we can prove one of it. Now, when you have, we have the bilinear. So the bilinear, let's look at it over here. So is this, okay. The bilinear, let's look at it over here. We saw that when you have C, okay, U, then plus D, V, okay, then W. This is what we saw, okay. Now, what we can do is all these things is going to be for the V1, and all these things is going to be what? For W1. So we can do substitution, all right. So what we can do is we have our 2 over here, then I wish maybe I'm coming, let me see whether I can get something to write. Okay, okay. Okay, so what I wanted to show you is we have CU plus DU, okay, then this is what I'm talking about. Oh, let me zoom this thing. Okay, so this is what I'm talking about. Okay, so where we see V1, we put this one there. Where you see W1, you put this one there. Okay, so when we do the substitution, we are supposed to get something like this. Let's go back. Yeah. You're supposed to end with something like this, where the scalars will be out, then we only have our vectors doing the multiplication, the inner product, sorry, doing the inner product. Okay. Okay. Now, I'm coming. I want something where I can do some of these things, but when I try to write, it doesn't go. I mean, it's this. Uh, All right, I'm waiting for my writing pad. It hasn't come yet. That is why. So forgive me. All right. So this, when we look at this, they're asking us, does it, follow inner product? For us to be able to prove it, we have to first prove one is what? Bilinear. Okay. So we have to prove it is bilinear. Then the second one, we have to prove that the positivity, okay, that uh, this, okay, is greater than 0. Then the last one uh, is for us to prove that it's also symmetry, okay, it's also symmetry, which is VW, okay, should be equal to sorry, VW, okay. All right. So these three, we can prove it from here. Okay, we can prove it from here. The first, which is the symmetry, is obvious. Okay, because we can change the values and nothing will change. Okay. Then this also we need to prove the positivity. Okay. That one too. If you look at it, uh, if any of the value is negative, for example, if any of the v is negative, are you going to get a negative value? And the bilinear, we will use this, which is we use the c, then v, okay, then plus your d, this is u rather, sorry, this is u, this is v, then comma our w. We use this one, okay, use this one to prove this. All right, so weighted norms are particular relevant in statistics and data fitting when one wants to emphasize the importance of certain measurement and de-emphasize others, as I said. So if you want to make sure something is important, you have to just assign weight to it. Okay. So when one wants to emphasize the importance of certain measurements and de-emphasize others. Okay, so if you want to make sure that certain measurements are of certain significance, you need to add a weight to it so that the model will also be able to I mean, uh, do it in a way that will provide or that will give you the proper results. Okay. All right. So the next thing we want to talk about is the unit vector. This unit vector, we did it in high school. All right. So when you have a vector, all right, we can we have a vector, we can calculate the Euclidean norm. So if you divide the vector by the Euclidean norm, that is our unit vector. Okay. And when you find the Euclidean norm of the unit vector, the answer is always 1, irrespective. Okay, the answer is always 1. But mind you, the vector should not be 0. It should not be a 0 vector because you know if you find the magnitude, sorry, if you find the Euclidean norm of a 0 vector, you get 0. So the vector divided by 0 will not make sense. Okay, you all agree to not make sense. All right. So we have this over here, and we can find the length or the Euclidean norm of it, which is 5. So by looking at the formula, you'll be able to calculate the unit vector. Okay. So this is my unit vector. So the unit vector is this. All right. So we've converted it. Here we know uh, the Euclidean norm and we divide it, and this is what we have over here. Okay. Now, the unit vector is very, very important. We will learn it. It's used in normalization, used to normalize. Okay. Yes, you use it in normalizing your data. Okay, if you don't normalize your data, for example, we spoke about the weight. If your data, some of them they are having bigger values, you don't normalize it, your model is going to pay attention to the one with the bigger values and it's going to learn a lot of features from there, leaving the ones with what? Less significant values. Okay. So most of the time it's good to normalize, and that is where the the unit vector comes in. And here, if you happen to find the I mean, the Euclidean norm, you get 1 for it. You get 1 for it. That means if you normalize, you will not change anything. Okay. So the last session, then I think we are done, is the inequalities. Now, these two inequalities are very, very important. Okay. They are related to bases. We'll talk about it. The orthogonal and also the orthonormal basis. They are related to it. Now, the first one is the Cauchy-Schwarz inequality, and we also have the triangle inequality. All right, guys, please, sorry, my professor called me. He called me several times, so I needed to pick the call. Okay, so sorry. Okay. All right, so this we're going to talk about these inequalities, and I mean it's something easy to uh, derive. All right, so this is the dot product, okay, or the inner product, okay, when you define in terms of angle, the angle between the two vectors. Okay. Now, when we take this, it can be expressed in a form of what? Inequality, and that is why the Cauchy-Schwarz inequality comes in. Now, what is this inequality? Let's find out. Now, when you find the cos of any angle, we expect the answer to be between -1 and 1, right? So we can rewrite this one can be written in this form. Okay, it can be written like this, where this is the negative part and this is the positive part, where this is our dot product. Okay, now because we are getting negative and positive, this can be written again as absolute value. So you see that this has been converted to this because this has been written as absolute value. So once have this in absolute value, that is the Cauchy-Schwarz inequality I have written so far. So what are we doing over here? What we are doing over here is that we we have our inner product or dot product over here, but it has been written in a more concise way, which we can use it in what is known as orthonormal basis calculation. We'll use that one over there. Okay. All right. So this is more concise. This is more, yes, concise, because here, when I find my dot product, it says it's supposed to be less or equal to when I multiply the two individual Euclidean norms. So that is the Cauchy-Schwarz inequality. So that one too follows a rule, and it states that every inner product satisfies this. Okay, and this is it. So what you see over here, this is the inner product. Okay, so the inner product is less or equal to when we multiply the Euclidean norms of the individual vectors. The individual vectors. All right. The next one is the triangle inequality. The triangle inequality. That one too is a build-up of the Cauchy-Schwarz inequality, just the build-up. So let's go and look at it. So we will find out why this is necessary next week. Okay, why we need this. Okay, so when we have this, okay, this is something I'll let you guys prove as an assignment. Okay, the proof is when you check books or online, they are all there. Okay, where we have this vein, then we will also have okay, okay. So we have this. We can prove it, which I'll ask you guys to do that as an assignment. Okay, which maybe you upload your results or you type. All right. Now let's look at this. So we have a vector. So we have a vector v, then we have a vector w. Okay, we can find their norms. So the v is 10, the w is 5. Okay, so if you want to use the triangle inequality, okay, this is what it's saying. Okay, so the when we sum the two and we find the norm, we are going to get root 13, which is less or equal to this. If you have a calculator, you can try it. You see that this is less or equal to this. And that is the triangle inequality thing that has been proved over here. Okay. Now, having spoken about the two inequalities, we want to talk about orthogonal vectors and orthogonal bases. Okay. For vectors, we said they have, geometry, which is Euclidean geometry, and we can have a vector that is perpendicular to another vector. We can have a vector that is perpendicular to another vector. Remember, we spoke about the linear combination, and we said you can have a vector and you can express it using several sets of vectors. And we came back and said we also have the linear independence, that when you have your linear combination, you shouldn't have a vector that you can express in the set using another vector in the set. We don't want that. We want all of them to what? To be independent. So because we want the vectors to be independent, that means when a vector is perpendicular to another vector, they don't point in the same direction, they point in the opposite direction. And this is where orthogonal vectors helps a lot with linear independence. Okay, so orthogonal vectors helps a lot with linear independence. All right. So from this equation, which we saw it right now from the triangle inequality equation, we saw this, that when you add the two vectors, you find their norm is less than or equal to when you find the individual norms of the vectors. Okay. But we said that when a vector is perpendicular to another vector, we say that their dot product vanishes. Why? Because the dot product becomes zero. Why does it become zero? Because cos 90 is equal to zero. As you can see over here, the pi half of pi or cos 270. Cos 270 is also what? Zero. Okay. So Yes, cos 272 is 0. So because of that, it will vanish. Okay. Yeah. So two vectors W and V are co-orthogonal if their inner product what vanishes. That means when you find the inner product, you get 0. I mean, that is uh, perpendicular to each other. So let's look at this. I have a vector over here, I have another vector over here. Okay, so these two vectors, when I find their dot product, I get 0. It tells you that this vector is perpendicular to this. Okay, perpendicular to this. And if these vectors are part of a linear combination, then you realize that they are independent. They are independent. Okay. So the orthogonality depends upon which inner product is being used. Now remember we spoke about the weighted inner product. So if you are dealing with weighted inner product, remember things will change. Okay, things might change. So here we did this calculation, we saw that these two vectors are perpendicular, that means they are orthogonal. But when we added it to, or when we made it weighted inner product, we didn't get 0, we had a negative 18. So that tells you that, I mean, when you are dealing with the orthogonal, you have to pay attention to what type of inner product you are using. Is it the normal inner product or a weighted one? Okay. All right. Now, one of the things that is going to help us a lot is orthonormal basis. Okay. You remember I spoke about linear combination, where you want to make sure that all your linear combination they are independent. That is a challenge we face a lot. And when you have a vector, okay, we said any vector, we can express it using our bases. So these are the bases. Now remember, we spoke about for the two dimension, we have what? 1, 0, and also what? 0, 1. Okay, we have this. Now, we said if you take the Cartesian plane, we can span the whole plane and get any vector using these bases, right? So when I have a vector, and let's assume I have a vector, let's say 1, 6, and I want to get the span of this vector, we are saying you can write it this way, where we have 1, okay, 0, then you also have, let's make it C1, then also have C2, okay, then 0, 1, okay. Now here, what I'm trying to do, or what I'm doing over here, is I'm building a system of what? Equation, right? Now, in order for us to be able to solve this, sometimes it becomes a little bit problem for you, in a sense that this one, because here this basis is obvious, okay, because here is 1, here is 0, automatically I'm going to say that you're going to have 1 is equal to C1 plus C2, then let's say 6 is equal to what? C1 plus what? C2. I think this one will even go back to 0 because when there's subtraction. All right. But how do you do this? There's a better way to do that. This is where the orthonormal comes in. Now, remember we did something in regard to the unit vectors, okay? So I have a vector over here. Look at 3 different vectors. Now these vectors, when I find their dot product, okay, I'm getting 0. That means the dot product between 1 and 2 is 0. The dot product between 1 and 3 is 0. The dot product between 2 and 3 also is 0. Okay, so we say that they are orthogonal. Okay, they are orthogonal to each other. Now, since they are orthogonal, that means they are also independent. Independent in a sense that I can form a linear combination of it. Okay, but how will I be able to determine that? That is where the challenge comes in. Okay, so when we have a vector, what we can do is have what is known as what? Orthonormal basis. When you are dealing with orthogonal basis. Now, when you are dealing with orthonormal basis, it's the same thing like you doing the unit vector where we try to do normalizing. Okay, so we try to normalize our vector. Okay, so you remember when you're doing the normalizing, which we have a unit vector, we have the vector, we divide by its magnitude, and we can get what? The unit vector here. Okay, so with this minute. Okay. All right. Now let's take there's this. I want to show this formula so that we're able to get this. You understand what I'm talking about. So we have this basis. We have this basis V1, V2, V3, all the way to V4. Okay. Now these bases are orthogonal. Okay. Now if I want to express how how do I say it? A linear combination, that is going to be a little challenge. For example, I have a vector over here. I have this vector, which is this the vector I have. Okay, and I want to express this vector as a linear combination. Now, to be able to express this vector as a linear combination using these values, this, and that. That means I'm going to solve a lot of linear equation. You understand? Because I'm going to write that vector then, which is equal to C then 1, then plus C V2 all the way to what? C4 then 4. Okay. Then after that, I will expand it. Then I have linear equation, which is systems of linear equation. Then I'm able to solve it, which is a whole lot of work. But once we know that the vectors are orthogonal and most of the bases are orthogonal, once we know that it's orthogonal, then we are done. Why? The first thing we can do is we will find the Euclidean norm of the basis. So here we find the norm of this, we find the norm of this, we find the Euclidean norm of this, we find the Euclidean norm of this. So that is what has been done over here. So we find the individual norms, right? Now, once we know the norm, the next thing is to go back and the vector that we have, which is the basis over here, we will convert all of them to unit basis. Okay, so that is what we have over here. So being converted to unit basis. Okay, so this has all of them has been converted. Then once we have done that, the next thing we can do is we'll be able to find the linear combination of the vector. How do you do that? How do you do that? We can do that when you pick your vector, which is this vector that you are dealing with. So let's go back to the formula again, then be able to see what I'm talking about. All right. So you have a vector, this, okay, which is we want to form a linear combination, as you can see over here. So in order to help us to get the scalar, we multiply the orthonormal basis by the vector that we want to express as a linear combination. So this vector we want to express as a linear combination, we first need to calculate, get our orthonormal basis and find the inner product between that vector and the orthonormal basis and be able to calculate our C. And that is what we've done over here. So once we know our orthonormal basis as we have done over here, we now have a dot product or an inner product between this and the vector, between this and this. Okay, and if you do the calculation, you will get that the C1 is 4, the C2 is this, and that and that. I wish you guys can do this so that I'll be able to prove one of it to make sure that it's actually correct. Okay, so let us try to make sure that this and this is correct. I think that's my last slide and I'm done. So let's do this then. There we go. All right. So write this one down. All of you write this down. Okay. So this is the U1. We are going to do cross dot product with this, which is then 4, -2, 1, and 5. Okay. So 4, -2, 1, okay, then 5. Okay. So you do that. So if you multiply this by this, you get what? 2, right? Then here you get -1. Okay, then here you get plus 1 over 2. Then here you get what? Plus 5 over 2. So I think this should give you, this one should give you 3. This also give you 1. So you get what? 4. Okay, so that is true. So you get 4 here. The same thing, the same thing, the same that. So you see that I have this vector and I want to express this as a linear combination. It is far easier if I use the orthogonal. Using the orthogonal is far better than you using what last week we spoke about, where you try to express the vectors and you want to have a system of linear equation. Having a system of linear equation is difficult to calculate because if your systems don't converge, okay, it's going to take a very long time, okay, and you're going to waste resources. But if you can convert it to orthonormal basis, then what we can do is that we can use inner product, and once we use inner product, we can use it on the orthonormal basis and we can get the C's. Okay, so these are the C's. So this vector has been expressed here as a linear combination. Okay. Now, how did we also get this? Now, this is a simplified version. You remember we saw that the unit vector is the vector divided by its magnitude, right? Which is the length of it, okay? The length of it. So if you go back to the calculation that we have here, we have 2 here, here we have 2, we also have this, we have this, okay? So when we come to, where is this values? Okay, so when we come back to, when we come back to, when we pick this, you know, I'm looking for the V1, 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 V1. So this is the V1. Okay, so the V1 is 2, V22 is 2. Okay. Okay. So if we look at the formula that we are having over here, a minute, need to get my writing pad quickly because I'm struggling too much. Okay. Let's go back to the orthonormal. Where is the formula? A minute, guys. A minute. So let's look at this. Okay. So here, if I want to find the vein, what do I do? Okay. What do I do? I multiply the linear, I mean the norm by the odds, by the unit vector, right? Okay. So okay. So if you want to be able to do that, then we have to go back and do that kind of multiplication. Okay, we pick our unit basis and we multiply it with our vector. Okay, yes, we multiply with our vector. And that is what you can see over here. So all the values that you can see, the 4, the -2, and this and that. That's what we express over here. Okay. Now, okay, so this brings us to the end. And next week, if God willing, we will continue, okay, and we will dive deeper into uh, projection, okay, why we try to project one vector on another. But we'll revisit this one again because we will need it to be able to get the span of our Imam Kami, be able to get the span of our set so that we can do any calculation with it. Yes, Imam, go on.